great honor to be here. It's just one of the best meetings I've been to in a long time. Really enjoying today. So I'm going to give a dry technical talk instead of making reminiscences. Hope that's okay. I thought that's what Arvin might prefer. So let's start with S. Yeah, S goes to MVVP. John. Love Mary. A complete derivation. Or so I thought until a few years ago, because I didn't go to school here. I went to school in Pennsylvania, but not here. So I was amazed to learn that, and began to do some of this, that I was amazed to learn that you can make more sentences like that. John got it in his head that Bill loved Mary, and you could even do more sentences, like John got it into his head that Jane found out by questionable means that Bill loved Mary. And you just go on, making more and more complex sentences. The derivation, you never knew when the derivation was over. So, but poor Mary, John, don't you love me anymore? I did. What happened to us? What went wrong? I don't know, John and Mary, they had locality. And then Bill. So I don't think the problem is with tag. I think it's I'm really bad at writing grammar sometimes, and I think maybe I should have done something more like John got it into his head that, then some substitution note, and then use the adjoining or something like that. And then in that world, if I'd done it that way, then John would be just somebody who gets stuff in his head, and Mary would be like, who's that guy? And Bill's like, that's just crazy John, let's go. Everything would be fine, I guess. Anyway, I know you guys know all this because it's covered in courses at Penn. But, so that's the end of part one of my talk. Part one was about adjoining, and part two, which is the only other part, also about adjoining. But let me go back. I think my students are much better at writing adjoining systems than I am, and I know one of my students, Steve Denif, built a nice system, and I know I said it, but at some point he got a letter from Arvin, and he came and brought it to me. Arvin invited me to give a talk at UPenn all the way across the country, something called a cliff talk, and he said, it sounds great, but I don't know if I can pay for my own ticket to go attend a lunch meet. And I said, don't worry about it. That's not how it works. This is awesome. He's going to pay for it, and you're going to go out and learn a lot of things. And he came back from that meeting just so happy. And I know Stuart Schubert's students who work on this have also been treated very kindly by Arvind. And Arvind's been very kind to me, too. I got back from a meeting this year, and in my email box was a letter from Arvind that said, I really enjoyed your talk and, that you gave, and I have a bunch of questions. Could I get a copy of your slides? So, of course, the first thing I did was I forwarded it to my wife with a subject line, exclamation point, exclamation point, exclamation point. I was just so happy. All right, so now part two, but I can't get to part two yet because first I want to say a word about machine translation. Which Arvind's always been supportive of machine translation work rather than treating it as a low-level engineering exercise. So everybody knows that this is how machine translation works. You start with the source string. You parse it into a source syntax tree, and then you get the meaning representation, and then you generate out a target tree and get the target string and show it to the user. Certainly everybody outside machine translation knows how machine translation works. And this left part, we call it the natural language understanding part of the translator, and the right part, we call it the natural language generation part. And just as an example, here you got that boy wants to go in English, and the semantic structure at the top. If you know feature structures, it's a semantic feature structure. It's which can also be viewed as a rooted, edge-labeled, leaf-labeled graph. So at the top, there's a wanting, some instance of a wanting. It has two roles, arg0, arg1. The arg0 is the wanter. That's some instance of a boy. Arg1 is the thing that's wanted, which is itself a going event. And the boy is also the goer. So he's the wanter and the goer at the same time. That's why there's only one boy node. That's why it's a graph, not a tree. And then generation can turn that into Chinese, or vice versa. You could go Chinese to English. Okay, so of course, some people, you might know about some projects in the 1950s that went more in the direct route. And even then, I think there's a famous information theorist called Warren Weaver that worked in that time. And he already realized, a bunch of stuff. So it's an interesting quote from him. So think by analogy of individuals living in a series of tall, closed towers, all erected over a common foundation. When they try to communicate with one another, they shout back and forth, each from his own closed tower. It's difficult to make sounds penetrate even the nearest towers, and communication proceeds very poorly. But when an individual goes down his tower, he finds himself in a great open basement, common to all the towers. Here he establishes easy and useful communication with the persons who have descended from their towers. Thus, it may be true that the way to translate from Chinese to Arabic, or from Russian to Portuguese is not to attempt the direct route, shouting from tower to tower. Perhaps the way is to descend from each language down to the common base of human communication, the real but as yet undiscovered universal language, and then reemerge by whatever particular route is convenient. So, I guess ahead of his time. Now, when Warren Weaver says descend to the common base, of course he means to go up. But for people who think of a tree as having its root at the top, or people who think that's a local minimum, I guess we're just used to this kind of thing. Hopefully it doesn't bother you. That looks like a local minimum to me, doesn't it? Don't want to be there. Okay, so let's look at that thing at the top. This is a semantic feature structure. So let's just look into what that, what we need is, a whole bunch of these, to really understand how to do the NLU and the NLG, we need a whole bunch of sentence meaning pairs, right? Just a vast database. Here's sentence, here's a meaning, and then people will come up with all sorts of methods. So if you were going to do that, you might define an abstract meaning representation language. You might write a 35-page guideline. You might make extensive use of prop-bank predicates, but you really want to cover all the words in a sentence. You might build an editor with logins, and you might get it to where people could write down the meaning of a sentence in 7 minutes, enabling very large-scale SEM banking. Okay, but let's not worry about that part right now. Let's worry about which part should we worry about? Oh yeah, just the semantic structure itself. What does it look like? So I think the key to the graph structure is that entities play multiple roles. So look at a sentence like, Pascal was charged with public intoxication and resisting arrest. So there's some charge 05 here, and we don't know who's doing the charging. That's the arg0 somewhere else. But the arg1 is definitely a person named Pascal. And what was Pascal charged with? Some conjunction of things, intoxication and resisting. What about the intoxication? It was located in public, and Pascal was the intoxicated entity. And then there's resisting, and who was doing the resisting? She was resisting too. She was resisting something like an arrest. And you might think we're done, but if you think about it, who was doing the arresting, we don't know. But who was getting arrested? Again, Pascal was getting arrested. So Pascal's playing 4 different roles in the sentence. And that's why as we type in the meanings of sentences, I think every other sentence, even if you just look within the sentence, has at least one reentrancy. The biggest one that we saw so far was 7 references to some entity. And these are not kind of syntactically motivated control structure necessarily. It's just any real-life reference that. So she's involved or potentially involved in all of these activities. Okay, so that's what makes the graphs pretty interesting. And if, how do you map in and out of graphs? How do we deal with these? We're really comfortable dealing with strings. Maybe too comfortable dealing with strings, so we know how to get k-best paths through finite state machines. We had to have forward-backward training and transducers and general toolkits and so on. And now I think in this century we've got a much better handle on tree automata and synchronous grammars for trees. You know how to take a English tree and turn it into a Chinese tree for translation, and how to compose transducers. Sometimes you can, sometimes you can't. How to do EM training and all that. I think it will be real interesting to learn better how to deal with graph structures. So how do you turn one graph into another graph, into another graph, into a tree, into a string, and how to use those, and maybe use them even for translation. So that's where I think adjoining, or at least adjoining-like strategies may prove pretty useful. So let's look at that. But first, I was looking at that with some students this summer, and they were all like, okay, but we need some data. I know data's coming, but we need some data. So I said, I got tired of their complaining that there's not enough graph semantic data out there. So I told them I would build them an infinitely large semantically annotated data set, which took me a week. So here it is. It's there's two predicates, want and believe, and there's two entities, boy and girl. And here are the semantic structures. The boy wants the girl. The boy wants to believe the girl. Boy wants the girl to believe him. Boy believes that the girl wants him. The boy wants to want the girl. I was just pressed yesterday to actually explain what that could possibly mean in the world. I got up to the third want, totally convincing, but the fourth one I'm still working on. The girl wants boy to believe that what? Almost. She wants him. The girl wants the boy to believe that she wants him. So we're kind of struggling with these mappings between these graphs and English because English is so weird. So the graphs they're kind of logical, right? The semantic structures. You got this one. So that's the boy wants to be believed. I forgot. So I created all this. I wrote a Turing machine to translate these into English. Okay. So here's the boy. So this is the boy wants to believe. This is the boy wants to be believed. So we just flipped arg0 and arg1 there. And then this is the boy wants the girl to be believed, and the boy wants to believe the girl. So previously, who knows who, okay. And then the boy wants to believe himself. So tiny little changes in semantic structure cause these big changes on the English side. And this is a nice little corpus because it stresses the graph aspects of things and forces you to worry about pronouns with K0 pronouns, passives, control structures, reflexives, long distance stuff. So he wants to want himself, but he wants to want her. So why do you use the self in one case? So it's a pretty challenging corpus there. Okay, so then we can look at how you might capture an infinite graph language. We're really comfortable capturing infinite tree languages and infinite string languages. But for capturing infinite graph languages, so what's the grammar? So there's been a fair amount of grammar work in mostly outside of this community, in the theory community. So for example, this DAG acceptor from Heart 75 is an interesting machine. So start with Q, and then you replace it with that rule on the left, and then you're going to replace another Q with another rule, and you replace that Q over there with an R, and then an R with a girl. Okay, and this is the key part. There's that rule at the bottom on the left. If you apply that rule, you get that. And you can do that anytime you want. Okay, but that didn't seem very local. So you build up this whole graph structure, and at any moment you can just take these two things and just put them together. So, but that is one way to generate graphs. But maybe some sort of adjoining strategy might be better. And there's these things called hyperedge replacement grammars. The nice thing about them is like tags, they have these context-free derivation for us. So you make multiple references to something can be generated in a single step and then kind of pushed apart. Okay, so let's look at how I can do that. So we're going to try to make that graph. But instead of just generating all the stuff and then, sticking the two B's into one B at the end, we're going to do kind of a joining strategy. So here we've got the first rule, elementary rule. There's a wanting by the boy, and what the boy wants is X. And X is edge non-terminal. So X really represents the something involving himself. So this rule means the boy wants something involving himself. And then we'll pick a rule that replaces the edge with whole subgraph, like So that's believe by the girl. And again, another X. So a non-terminal can make another non-terminal edge. Just like when you adjoin a VP, you can create another VP that you can also adjoin. So, but this is in the semantic realm now. So then we can replace this X, which is something involving the boy, with this. So that's a wanting of the boy. And now that's the way we generated this thing. And this is something like the boy wants the girl to believe that he is wanted. Reasonable. And this that was just one whole generation of a graph. Let's just do one more. So this is, again, the boy wants something involving himself, but this time we're going to place the X edge with another X edge, but this is a hyper edge because it has two tails. So this is what's wanted by the boy. What he wants is a red thing here. Some believing by the girl of something involving both him and the girl. So the boy wants the girl to believe something involving them both. And now there's rules that replace hyper edges as well as rules that replace it. So if you want to replace that hyper edge, then you can now do it, pick some rule and replace it. And now we've got more complex graph where the girl plays two roles and the boy plays two roles. And so that's some mechanisms for generating infinite sets of graphs. These things are nice. They can also do, like tech can do the kind of sister adjunction, so you can build out things horizontally as well as vertically, and that's important because these are very flat structures. Okay, so that's all about graph acceptors. And then where we started was trying to then build generators for an understander. So we want to take those graph structures and express them in English. And even for people, it's hard to express those in English. And hopefully we'll learn lots of rules about how to do that. And the mechanism, I think, is still open. So asynchronous hyperedge replacement grammars is certainly something that should be investigated. So that's where, on the semantic side, you say the boy wants something involving himself. And then on the syntax side, you produce a bit of syntactic fragment. The boy wants infinitive. And then when you replace the X, you also flesh out a little bit more of the syntax side. And then replace that X. And now we got the boy wants the girl to believe he is wanted on the English side, and we built up the semantic side. And you can use these synchronous machines to go either way, the NLG or the NLU. Okay, so hopefully, I think there's a lot of kind of machinery out there now, unification-based grammar, graph grammars, graph-to-tree transducers, graph acceptors, hyperedge replacement. And I think once we have a lot of data about here's strings and their meaning, string, meaning, string, meaning, string, meaning, that some of those kind of formalisms will kind of turn out to be excellent fit for that data, and other ones maybe not so much. And part of being an excellent fit, of course, is not just explaining the linguistic data, but having efficient algorithms so that we can really use them in full-scale systems. Okay, so you could see that second part of that talk was hoping that adjoining has a great role to play. So thanks for the adjoining.
I have a question. Going back to your last slide, when you were listing the graph automata algorithms, this actually brings in something from Julia's talk. I heard you use the word vacation.
Did I say vacation?
But I must have it didn't make sense in the context. It was something like a vacation transducer or something like that.
I think we could all use a vacation transducer. Did anybody else hear that? I didn't hear that.
Right, other questions?
So the column on truth, there's some history between tag and truth. So where does tag fit into those?
Oh, you should ask Stuart Sheeber. Is there a
So there's a tight connection between certain kinds. So tree automata, there's all kinds of different tree automata. Page-long drawings, all the different relations. But certain kinds of them are equivalent to certain kinds of tag, which is interesting, and we make them synchronous. Synchronous tags tend to be related to bits and pieces of the tree. There's formal language literature that look at those kinds of things. Yeah, very tight.
So synchronous grammar tends to think of there's the kind of the hidden part, and then which is the derivation, and then you get out the inputs and the outputs. And tree transducers take things a little bit more literally and try to just go from the input to the output. But the way to connect them up theoretically, I think it's fair to say, is you think of it as two kind of transducers, and you go up to that hidden part and then back down out again. Yeah.
This is a crazy comment, but I'll make it anyway. So there's a whole line of
Fernando, could you go to two microphones
Where
so
are
we
they?
please record this?
Okay. All right, I will. Okay, there are my. So as you there's this line of work that's not very well known on learnability of automata structure from, and this is kind of the cognitive, where you can show that you can do strictly more powerful things if you start with reentrancy than if you only do state split. If you do state merging, you can do strictly more powerful languages. And I'm wondering whether there's something to be drawn from those ideas to the right-hand side of your graph there.
This is kind of classical learnability, not the kind of statistical EM type things, but whether.
Really, actually, because there's all the work, the merging versus state splitting. It's sort of it's not quite as well known as it should be. But it's kind of interesting because I was listening to your talk and thinking, starting with reentrancy is more interesting even from the point of view of learnability than it is from the point of view of computation.
Yeah. I think that's a great idea.
Questions? Then I guess we'll thank the speaker and